we'll take one more minute since participants are still joining, and we'll start with the next session. Yeah. You have a query, please. Maybe you can check once if the questions are same or different, like depending on the question pool from where the questions have been selected. There might be few questions which might be different in both the sessions, or you might find two similar. So it ultimately depends, and I'm really not sure because I haven't coordinated yet with the other TA. So maybe you can check it once, just for the sake of it, if both the sessions are similar. But yeah, both the sessions will definitely be problem solving sessions. But yeah, the questions, it ultimately depends on the question pool from where we are selecting the problems for these sessions. Okay, so we have still students joining. Maybe we'll wait till 6:05. Let all the students first join, then we can start. Okay, it's already 6:05, so let's begin today's session. Kindly let me know if you're like if my voice is not clear, or if something you find something difficult to understand. So I formally welcome you all to today's live problem solving session. This is the first problem solving session for the course Analog Electronic Circuits, which has started already from 24th July. And I am Dishada Devi, a PhD scholar and PMRF fellow from IIT Gandhinagar. I'll be conducting this particular session, live problem solving session, on Monday 6 to 8 every week till October. So welcome on board. Let's begin this session. So you might have already gone through the course policy, right? Course layout. So the layout is as follows. Sorry. Okay, so for course notes, like there are lecture series which are available online. So you will be getting that. Along with that, the transcript is already generated. For this particular session, whatever notes I am preparing, I'll share that with you. So you'll get the PDFs of this particular session, as well as the recorded lectures will be uploaded on YouTube. So you can access those lectures. So you'll have the lectures both in hard copy as well as soft copy as far as this particular session is concerned. Is it clear? I'm audible clearly, right? There are no glitches.
Yes, yes.
Okay. So moving ahead with the course policy. So this particular course is designed for 12 weeks. And first week we'll talk about nonlinear circuits, diodes, load line concepts, and just the introduction to MOSFETs. Then in the second week we'll talk about DC operating point, biasing of MOSFETs, small signal models. All these topics will be covered in the second week. Third week we will have Thevenin-Norton models, common source, common gate, common drain configuration, which are basic amplifier configurations for the MOSFET. Then we'll go with the advanced versions of MOSFETs like source degenerate and cascade circuits. We'll then move to current mirrors, biasing circuits, and constant gain circuits. So for designing better sources like better current source and stable voltage sources. Then we'll move to differential amplifiers, which will have where we will perform common mode and differential mode analysis. We'll talk about CMRR, etc. We'll then talk about folded cascode in differential amplifiers. Then we will move to feedback circuits, feedback amplifiers. Then we will talk about high frequency models for MOSFETs. Then we'll do pole to zero analysis, Miller theorems, phase margin, gain margin, unity bandwidth, compensation concepts. We'll go through these concepts in the following week. When we talk about 11th week, we'll go for voltage regulators, LDOs, stabilities of regulators. And in the final week, it might be power amplifiers or audio amplifiers, all these amplifiers. So you may expect the problems corresponding to each week. You will have a problem set, and even in live problem session, we will work on the problems. Topics which are given for that particular week. So since this is the very first week, so let's start with few basics. So when we talk about electronics, what comes to our mind? Like, what is electronics? Let's make this session very interactive. You can be as free as possible. You can ask as many doubts as possible. So let's try to get maximum out of these sessions, okay? So what do you understand by electronics? Like, what comes to your mind when you think of electronics?
Yes, I have an idea what comes in your mind when you see electronics. I feel you are talking about very tiny and small things are doing very interesting functionalities.
That's a good point. So very small circuits, right? Very small circuits or systems. One of the major advantages of electronics is very small circuits and systems. What else comes to your mind when you think of electronics? What is electronics?
Low value of currents and voltage.
Sorry?
We deal with low values of currents and voltage.
Low currents and voltage. Yes. Low and what else?
Electron movement, ma'am.
Sorry?
It is the study
Movement of electrons.
Okay, so there are two people who are talking and both are getting merged, so I'm unable to understand.
It is okay.
Yeah,
It is the study of electrons in semiconductors.
Ma'am, some noise are coming from your side, I guess.
I'm not really sure. So what type of noise is it? Is it
Noise
like
in the sense some
electronic
disturbances
noise
through mic.
Hello?
Yeah, it's like when you are connecting and 3.5 mm kind of disturbance.
My mic. Wait a moment. Maybe I'll change my earphones. Hello? Hello?
Yes, yes.
Yes, ma'am. Now it is clear, I guess.
Voice not audible, right?
Your voice is a little bit low.
I guess there is some issue with my earphones. Hello,
Yes, I can hear you. I can hear you.
you can hear me, right?
Yes.
Yes.
Voice is little bit low, but
Okay, my voice is a little bit low.
uh,
Mhm.
Okay. Actually, I guess there is some issue with my earphones. Maybe I will check it for the next time. Anyway, am I audible? Like, is it reasonably, audibility is reasonable? Like, can you hear me?
yes, yes.
Okay, okay.
Yes.
Yeah, so,
Yes. But please, can you please try to raise your voice a little bit?
okay, should I raise my voice? Okay, maybe I will talk a little louder.
Yeah. Yeah.
Yeah. Uh, okay, somebody raised hand. Sankaran, you raised hand. Do you want to say something?
My question is, will this session repeat tomorrow, or today's and tomorrow's sessions will be different actually?
Here's the point. So both the sessions are problem solving sessions. Both are tutorial sessions only. The only difference that you will see is there might be few questions which are different in both the sessions depending on from where we have selected our problem. The
Okay.
question pools might be different, so you might encounter different problems, or we might get you might get the same problems also. So maybe you can check for once in a while, or you can attend any one that will also do, because anyways we'll try to cover almost all the concepts which are basically considered in that particular week. So you need not to go for both the week, like both the sessions. You can attend any one of them, because
Okay.
both will be problem solving sessions only. So you'll get problems and they will be corresponding to that particular week. So there won't be any issue. Few questions might be different, or even few values. Sometimes questions are even same, but just the values are different. But the concepts will be hopefully the concepts will be considered in both the sessions. So you can attend any one of them. You don't have to go for both. Yeah.
Thank you. I have got just one more doubt. Like in assignment one, like I'm not getting some of the values. Yeah, I guess you are the TA in charge. So
No,
is there
I'm
any
not.
are there any discrepancies in assignment one? Because any question that uses the diode equation,
Yes.
I'm not getting I'm not getting the options. So I wanted to clarify that because I've spent too much time on that.
Okay, so I'm not the TA in charge. I'm only conducting these online sessions. So I have not prepared the problems
Okay, sorry.
accordingly. But yeah, I guess you are asking. So there might be some dilemma with the value of VD, right? On voltage for your diodes. In that case, you might be facing the difficulty. Like in problems, on voltage is not given. Something like that is the issue.
Yep, yep. Like thing is like numerically whatever value I get, right? Like the currents corresponding to that I cannot get in the options, and even the like dynamic resistance is also like quite off the mark in all the problems. And last and this counts for nearly 7 out of the 10 points. So yeah.
Uh, Actually, I am considering those problems. Maybe you can look through the problems the way I solve. And if you can think like there is some discrepancy in your method of solving the problem, that might be one. Or if you really think that there is some issue, you can definitely raise a problem in the forum, right? You have access to the forum, right? So in the
Yep,
forum,
yep. I have put it in the forum. I've not got a reply, so that's why.
yeah. So actually, the forum is handled by the TAs, so they definitely revert you back, and they are the people who actually design the problem. So all the problems that you actually see are designed by the actual TAs. So we are online TAs for conducting tutorials. but they are the ones who have actually designed the problem. So you might get better feedback from them.
Okay, I'm sorry. Yeah.
Yeah.
It's okay.
Yeah. Okay. So coming back to the problem where we were earlier, so we were talking about electronics. So we said like these are small circuits, low voltages and current. This basically consists of semiconductors. What else comes to our mind when we think of electronics?
Charge particles.
Yeah. It's ultimately charged particles flow.
Control systems.
Sorry?
Control systems, controlling systems.
Control systems.
Controlling functionalities.
Control systems, controlling functionalities, and there also we'll talk about few systems which are controlled and which are not controlled. So, but okay, let's try control. What else? Anything else? Anybody? Anything?
Dynamics of charges.
Yeah, charge
Dynamics of
particles
electron.
and their dynamics. Yes, charge particle dynamics. What else? Anything that we are missing here? You want to add?
Transistors.
Okay. So I guess more or less we have considered electronics. Now talking about components in electronics, right? So what are the components that we use when we are talking about electronics? What are the components that we generally see in an electronic circuit?
Resistor.
Resistor, capacitor, diodes.
Amplifier.
RLC, diode. Okay, so amplifier is not a component. Amplifier is a circuit. So there is a difference. If it is a single component, we call it as a component. If it is a
Transistor also?
Yes. If it is a combination of
voltage sources.
Yeah, voltage sources, voltage and current sources. What else?
Almost all the passive and active components.
So we have got some new terms, right? Passive and active components. So we'll elaborate this as well. But any components that we are left with other than RLC, diodes, transistors I'm considering both BJT and MOS. Anything else that we are left with?
Transformer.
Electrical device, I guess.
It's an electrical device. It's not an electronic.
Electrical device.
Yes. So anything that comes to your mind other than these as components of electronics?
Yes. Why we didn't consider the resistor as an electrical device?
Sorry? Yeah. So see.
Electrical as well as electronics.
Yes. So these are the basic components which are used in electrical as well as electronics. And not L, but R and C are not
absolutely
the R and
electronics.
C and not the R and C that we actually see. So we see like electrolytic
time
capacitors.
Constant?
Sorry.
We talk about time constants of any circuit, which is the combination of R and C.
RC circuits.
RC circuits.
No, so what I was talking about is components, right? So when we say RLC, so in electronics, when we talk about chips, so these RLCs are not the way you know the RLCs, okay? So how do we know our resistors? How do the resistors look? Everyone has performed lab experiments, right? On breadboards. You have seen resistors, am I right?
Yeah, we have seen the physical
so these
resistors.
are basically like color coded, and we get our values of resistance from those color codings, from the bands and everything. When we talk about capacitors, we have seen like electrolytic capacitors or ceramic capacitors. But actually, when we talk about in chip, if inside an electronic chip you want to have a resistor, you cannot have that big color coded resistor inside your chip. So for that, even the resistors and capacitors are made in nano dimensions. Currently we are in nanometer scale, right? So all these components are designed and made in nanoscale. And to be very precise, R and C are made using transistors. This is very interesting to know. And in your chips, the basic fundamental unit that you have is a transistor. And each and every circuit and component inside your chip is designed using a transistor. And how these transistors are made, we call it CMOS technology. And through this CMOS technology, all the transistors are made, the connections are made, and you get the chip out. And so yeah, this is something very important and interesting to know, that inside your chips, each and every component is made up of a transistor, and to be very specific, they are MOSFETs. So that is it. But the functionalities are different. See, every component is a MOSFET, but a MOSFET will behave as a capacitor when it is designed a certain way. It will behave as a resistor when it is designed a certain way. Not even design. When I say design, it means biasing it a certain way. If you bias it a certain way, it will act as a capacitor. If you bias it other way, it will act as a resistor. If you bias it even in a different way, it will act as a proper MOSFET. So that's how your chips basically work. Now, okay, so we have covered almost all basic components which are there in electronics. Now talking about passive and active components. So we all know the components are basically divided into two types, active and passive. So what do we understand by active and passive? What are passive components and what are active components? By definition, what do we mean by passive and active components?
Components
Active,
absorbing
which
energy.
amplifies.
Sorry.
Components which absorb energies are active, like absorbs power.
Components
No,
They are
Or
passive.
take
I'm
power as an
sorry.
input. Those are passive. Or generates power.
The
Those are active
elements capable of
elements. Yeah.
amplification are passive.
Amplification, which we
Uh,
in our
may I know why we are so focused on amplification?
Or power gain.
we were taught like that.
Okay.
I
So,
think because we are in an analog course.
so why not oscillators? Oscillators are
BJT
also
and
analogs, right?
MOSFETs generally follow amplification.
But
Or
we get oscillations also, right? Oscillator behavior from these components. No? So why not
yeah.
oscillations, oscillators? Why only amplification?
Because in oscillator also you will find an amplification and amplifiers. Amplifiers are the fundamentals.
Uh, yeah, the video will be posted immediately after this session on YouTube, and the link
Will be
shall
very
be
helpful.
shared
Yeah.
with you. So, okay, so I'll let you know very basic, like, I'll let you know very basic definitions for passive and active components. Okay. So, what is your take on diode? Is it an active device or a passive device?
Passive.
Passive. Passive.
Okay. Yes, it's a passive device. So, when we talk about passive device, we have RLCs and diodes. Whereas when we talk about active device, we have BJTs and MOSFETs. But by definition, what do we mean by active and passive devices? So passive devices or passive components are those which have two terminals. They, first of all, they consume power. Active devices also consume power. Passive also consumes power. It's not like active devices don't consume power. But the major difference between these two is the outputs of active devices are controllable and programmable. Which means, see, if you understand a MOSFET, it basically majorly has three terminals. Actually, it has four, but there are three functional terminals, right? Source, drain, gate.
Gate, source, and drain.
Similarly, your BJT also has three terminals: emitter, base, and collector. Now, let's say if I fix my voltages for emitter and collector, or I fix my voltages across drain and source, right? Now, will I get same IV behavior if I apply different gate voltages or if I apply different base voltage? So if my
Can you
drain,
It varies.
it
repeat
varies.
the question, please?
So the question is, let's say I have fixed my drain to source voltage, VDS, we call it VDS, right? And I have fixed my emitter to collector voltage, which is VC, right? Now I have my VB, I have my VG, which are variable. So my question is, if I am varying my VD or VG, will I get the same IV characteristics?
No, it changes.
It
It
will
changes.
change.
But if you have an R, L, C, or even a diode, whatever voltage you apply across these two terminals, you will always give a single value of current. They are not programmable. Are you getting my point?
Yes.
So the
Yeah, it's
basic
clear.
difference
Absolutely.
in passive and active is, in active, like all the active components have a programmable node, a programmable terminal with which you can change its electrical behavior. Okay? But when we talk about passive components, you don't have those type of terminals, and for a fixed voltage, you will always get a fixed current. But in like active devices, for a fixed voltage, you might get different currents depending on that program terminal voltage. Is this clear? So that is the basic difference between passive and active components. Okay? Am I making sense? Is this clear to everyone?
Absolutely.
Yes, ma'am.
Yeah.
Yeah.
Okay. So now, see, we have talked almost everything about components. We have discussed active and passive components as well. So now, since components have been discussed, so what comes next? It's ultimately the circuits, right? So from here, we'll talk about circuits. So these circuits will be majorly designed using active components, because active components will be the major part of the circuits. And based on these components, what are the circuits that we are going to design? We'll design amplifiers, oscillators. Majorly these two topics will be covered, and majorly we will focus on amplifiers and different types of amplifiers. Oscillators is not actually considered in this particular course, but when we talk about analog circuits, oscillators also come into picture. So maybe we are not going to cover it, but I'll cover this particular thing in the introduction, so we have a complete idea of this particular course and this particular domain. Okay? So when we talk about amplifiers, so what do we know about amplifiers? First of all, they amplify the inputs. This is the basic thing that we know. And have you ever seen amplifiers? Like, have you ever seen or encountered any amplifier in your life?
Yes.
Where?
In our labs.
No, not in lab setup. I'm talking about in your real life.
Microphone, no?
Yeah,
Public addressing system.
speaker.
Yeah, sound
Public
system,
addressing
your
system.
mics, everywhere you use amplifiers. How does your speaker work? So there is an amplifier behind it. So that's how your speaker works. So we have all used amplifiers consciously, subconsciously. So in this amplifier, so the basic idea is it amplifies the input. Now, in amplifiers, there are, first of all, there is a feedback system that goes into this amplifier circuit. which basically helps in amplification. And the feedback system that is used for amplifiers is a negative feedback.
Negative feedback.
Yes, it's a negative feedback. which
Oscillators, we go for positive.
Positive.
Yes, so that is the one of the major differences between positive and negative feedback and their uses. So here we have negative feedback. What else we know about amplifiers? So amplifiers are of different types, like single stage, multi-stage. We'll talk about these all. So basically we'll consider all of them: single stage, multi-stage, differential. So these are like most basic type of amplifiers which are designed using MOSFETs, and we'll look into all these amplifiers one by one in the coming weeks. And okay, so when we talk about amplifiers, we only say it amplifies, but there are certain configurations which are not used for amplification, rather they are used as buffers. Okay, so in amplifiers there is another type. It's a type of amplifier. It's a configuration in which we connect our MOSFET, but it does not amplify your signal, rather it acts as a buffer. And we'll talk about buffers also a little bit, because it is very important to understand a buffer, and it plays a key role in designing your circuits. Okay, so buffers. Now when we talk about oscillators, so one major difference between amplifier and oscillator is feedback. What else is very different between these two, amplifiers and oscillators? What do you know that is like different in amplifier and
Stability, ma'am.
stability?
Negative feedback has more stability compared to positive feedback.
Yeah, that comes with the feedback. So I'm asking,
Yes.
is there anything that you find different between an oscillator and an amplifier?
Yes, ma'am. In the negative, I mean, in the oscillator, that feedback will get added to the input. Where it comes to negative feedback, it will be a difference between input and the feedback.
Yeah, so that is the definition of feedback itself, right? Negative feedback and positive feedback. When we say, we understand it's
Yes.
the same thing. I'm talking
Oscillator
about
doesn't involve inputs. Inputs.
inputs. What about inputs?
Amplifier require input. Oscillators doesn't have an input.
Yes. So it's no input required. So we don't give any input to the oscillator. So a basic question from my side: if we don't give any input, how are we getting output in the oscillator? Is it possible that you don't put any effort and you get the output? Is it really possible? What do you think? What's your take?
External noise.
So where does that
Noise.
Where does that noise come from? Okay. So yeah, it amplifies. So basically, your oscillator picks up the noise that it gets from maybe thermal agitation of your component, because we are always constantly providing it supply voltage. So there might be some noise in the supply voltage which it picks up, and it resonates it and we get a oscillating signal. Or it might be due to the thermal agitation of charges inside your device, which basically causes noise and you get your oscillation. So it is actually some or the other type of noise that leads to your oscillations that you get, or the signal that you get out of an oscillator. But so since it doesn't take input, so what's your take on power consumption? Like, oscillators consume power? do oscillators consume power? We know that they don't take input signals, but do they consume power?
Yes, for
I guess
sure.
yes.
Yes, because input signal and power consumption are two different things. When we say input signal, it is some sort of signal which is provided through the input. But for your transistors to work, you have to first provide them with the stable voltages that we call VDD and ground, right? We have to supply and make or put our oscillators into a certain region of operation so that your transistors start working. And for that, you will need power. And that is the major, like, that is what contributes to power consumption. It's not your input signal. Sometimes input signal is also, like, input signal also consumes power, like input transitions and everything also consumes power. But the major power that comes out for this power consumption is from your VDD and ground. So, so that's the main point why I wanted to pinpoint this especially is these are two different things. So please don't confuse with your input signal and power consumption. These are two different things. So when we are on the same terms, so let me talk also about biasing. Have you heard of this term biasing? In
Yes, in
context to
BJT.
BJTs and MOSFETs. Have you heard of this term biasing? So what do you
Yes.
understand by
Yes.
biasing? What is biasing?
Making the
But
device to be in one region, one of the three regions what are available.
Triggering the
bias,
device for certain work.
biasing means applying a certain potential on the terminals in order to have the device working in a certain operation region.
Yes. So first of all, we are applying voltage for your device to act in a certain region or to fix it in a certain operation region and to get the respective functionality out of it. That is the idea of biasing. Now, okay, first question. Is biasing AC or DC?
DC.
DC.
Yes,
DC.
biasing is always DC. Biasing is always DC. Now, but if you want to get like amplification, so amplification you do of analog signals, right? DC signals also can be amplified, but majorly you amplify your analog signals. So that means analog means AC. AC signals are amplified. So,
I have a question.
so yes, please.
Yes. Do we have biasing in diodes or not?
Do we have biasing of?
In diodes. We say sometimes the diode is forward biased or reverse biased. So we have biasing in diodes, right?
Okay, forward bias and reverse bias. See, that is also biasing and it is also a DC fixed voltage, right? And we do put our transistor or our PN diode in forward or reverse bias depending on our DC voltage. But the idea is when we talk about transistors, we talk about small signals. Okay, so there are many things that are there when we talk about basics of these electronic components. So when we want amplifier action, when we want amplifier action or amplification from our BJT, we always want a linear amplifier. We always want a linear amplifier. Have you ever heard of linear amplification or linear amplifier? Any one of you? Do you have any idea?
I heard about linear integrated circuits, yes.
Linear integrated circuit is different. I'm talking anything about linear amplifier or linear amplification? Have you heard anything in this regard?
No, no.
No. Okay. So let
Yes,
me.
ma'am. That means that depends on the order, ma'am. For example, if you take common source amplifier, if we, means that non-linearity while we are designing that based on second harmonics, we should design that con- that may act as a linear amplifier.
Okay. So you're going into a bit technical thing. I'll explain it in a very layman term. Okay. So when we talk about linear amplification, that means let's say I'm giving input as this particular signal. That is my input to my amplifier, and I want an output out of it, which will be definitely amplified, but I want linear amplification out of it. That means each and every point of my input signal should be amplified with the same amount. So like so let's say A, B, C, D. I have 4 points. So if suppose I get an output like my A has been amplified by 2 times, but my B has amplified only by 1.5 times. My point C has amplified by 3 times. My B has amplified. It has not amplified only. It has remained on its own like at 1, the same order of 1. Now when this happens, so you'll basically get an distorted signal. Can you see something which is very abrupt going over here? Rather,
Yes.
if I
Yes.
say that I want to get a linear amplification, that is, I want my each and every point to be amplified by, let's say, 1.5 times. So can you see the change in the signal structure? Like your output has completely changed, its shape has completely changed. And when we say like the shape has changed, that means basically the information has changed, right? Because ultimately it is the shape that carries your information, right? So
Ma'am, that is due to intermodulation, right?
sorry,
The change is due to intermodulation, right?
this change, intermodulation,
Third order intermod.
we can say it's like I don't know how to say it in electronics terms, but so it is basically as somebody was saying, like higher order terms comes into your picture when you are going for amplification function, or it's like when harmonics come into your picture, they basically distort your signal. So it's like multiple harmonics of the same signal are coming into picture, then your information gets distorted.
Basically, it's a distortion kind of thing.
So it's basically a distortion, yes, because you are unable to retain the shape as it is, right? And it is the shape that actually has the information about your signal. So when you want your information to be transmitted, you just want its amplitudes to be changed. You don't want any changes in form of their frequencies or any type of manipulation in your amplitude, because the moment your amplitude changes with different fractions, it basically distorts your signal completely. So it's a type of distortion. So for amplifiers, you always want linear amplification. And when we say linear amplification, that means there are 2 things. First of all, no change in frequency. That means if I give, let's say, a 50 hertz input signal to my amplifier, I should get my output signal as 50 hertz signal itself. It should not go to 60 hertz or 70 hertz, or it should not come down to 20 hertz. That's not, that will completely distort your information, because the change in frequency is also a distortion. The change in amplitude is also a distortion. So we don't want any type of distortion. So that is the basic idea. So when we say linear amplification, that means no change in frequency and same amplification factor across the signal. So we should get the same amplification factor across the signal and same frequency. Now, what basically happens is, when we look at our MOSFET IV characteristics, which is ID VG characteristics, we all know that this is quadratic in nature, right? Or is it exponential? What is the behavior of IDVG? I'm talking
Ma'am,
about MOSFETs.
Quadratic.
Yes, for MOSFETs it is quadratic. Whereas when we talk about BJT, it is exponential. So that's the difference that we always have to keep in mind. So this is quadratic, right? Now, what happens is, majority of the time you are giving input via your gate or source. So it is actually VGS. So you will always give your input from gate or source terminal. So it is considered in VGS, right? So if you look at it very carefully, so if I take this point and this point, so my input, let's say, is this big, what will happen to my output? Let's see. So my output will come like this. So can you see something? Like for a symmetric, almost symmetric, like this is, okay. So this is a symmetric input signal, right? But with symmetric input signal, when we are taking the corresponding output, we can see that the peaks are smaller than your dips. Can you observe, everyone? Can you see this? So this is what I am talking about when I say non-linearity. But we also know that as we reduce this channel as small as possible, so we can convert each and every system to a linear system when the size is comparatively very small. Even an exponential system can be represented as a linear system, considering the limits are very small. We all know that, right? So similarly, the Akshaya has raised hand. Akshaya, do you have any doubt? Maybe you can unmute and ask. So this is where the nonlinearity comes. Now, when we reduce this domain to very small region, so in that particular region, it actually behaves as a linear, like linear amplifier, and gives us a linear performance. So that is where actually the difference comes in the, if I say in a diode and a MOSFET operation. So let's say if there is a MOSFET and you want to make it as an amplifier and a linear amplifier, the actual input signal that you can give to that MOSFET is in few millivolts. It's like 100 millivolts, 200 millivolts maximum to that. And sometimes it's even lesser, it's like 20 millivolts, 50 millivolts, depending on the design of amplifier and these things. But in case of a diode, that restriction is not there. And considering diode is a passive device, so you don't have this controlling issue, which is basically coming because of VG. So in diode, you can give plus 5 volt to minus 5 volt signal, and there definitely you won't be getting the amplification operation. You will be getting a clipping operation or clamping operation out of diode, considering how you design the circuit. Yeah. So when we talk about amplifiers, we need to think of this linear amplification. So always we need to make sure that the inputs that we are providing to our amplifier, which is basically an AC input, it should follow the range where it keeps your amplifier in linear range. Okay. And maybe in next session I can also explain you like how to find this linear range also, because today we have already lost a lot of time. So maybe in next
Ma'am,
session we can discuss how
ma'am,
to
ma'am,
get this range. Yes.
ma'am, for example, if you take a common source amplifier, if you means minus GM into R naught, if it is a resistive element, a load is
Sorry. Come again.
common source amplifier, ma'am.
It is a common source amplifier.
Yeah, if it is common source amplifier, how can we say it is a linear amplifier? Means gain should be minus GM into R naught, no? How can we say that it is a linear amplifier based on the amplification factor?
No. So first things first, when you are talking about formulas, in formulas you will not basically see the implication of linear amplifiers as such. All the formulas are derived considering your amplifier is a linear amplifier. When we are practically using our amplifier, we have to keep this in our mind that our input signals should fall in the range so that the amplifier works as a linear amplifier. And it is very important. Otherwise, your signals will be distorted, your output will be distorted, and you will basically lose your information that you don't want, right? So that is the idea.
Yes, ma'am. That was only. Yeah. How can we means in Cadence I am implementing, ma'am. How can we say matlab afterwards if it is not linear, there would be second order, third order. That thing I know, ma'am. If you take it as a transfer function, input and output, definitely if it is a LTA system, we cannot get a exact. We will not able to amplify the signal. No? It's definitely that the non-linearity term is present in the black box. Means matlab, the transfer function is present. Non-linearity is present. The first order, second order. What we derived is first order. No? Afterwards, there would be second order, third order. How can we say it is a linear amplifier?
So that is what I am saying. If your input signal is very small, let's say your peak-to-peak input signal is 10 millivolts.
Yes, ma'am.
So 10 millivolts is actually very small signal, and with 10 millivolt signal, you will definitely get linear amplification. Or let's say your input signal is like 1 microvolt peak-to-peak. It's definitely a very small signal, so your output will definitely come as a linear amplifier. Or your output will be completely linear. And you can observe this also in your cadence. When you see your output behavior, you can clearly see your sine wave getting distorted. Either it gets truncated or it gets flattened, or you can see different types of behavior, but it won't be a sine. But the smaller the signal that you provide, the better sine wave you can retain. The better shape of sine wave you can retain. So that is the idea.
Okay, within means that input range, ma'am. You were saying about that input range, no?
Yes, it depends on the input. So what you can do is you can change your input sizes. So you can change your peak-to-peak input sinusoid to, let's say, 1 volt peak-to-peak, and 1 volt, 2 volts peak-to-peak, 5 volt peak-to-peak, and you can come down all the way to, let's say, 1 microvolt peak-to-peak. And you can clearly see the differences. And you can zoom and see how the sine wave actually retains for smaller amplitudes. But when you go for larger amplitudes, you get the distortions in your sound. You can clearly observe that.
Yeah. Ma'am, means within a means if we are designing the amplifier, that definitely MOSFET should be in a saturation region.
Yes.
Okay. Afterwards, there would be a limit, ma'am. For input also, if you increase beyond the input, then MOSFET will go to into triode region. Right? There is a possibility, right?
Yes, that is also there. That condition is also there. And yeah, this is one more important point for amplifiers. Our MOSFETs need to be in saturation region or in active region. for BJT.
Yes, ma'am. Today on a morning session, I went through Rasavi, ma'am. In saturation region, the Ohm's law will get failed, no, ma'am.
Sorry?
In saturation region, Ohm's law will get failed, no, ma'am.
Yes.
I mean, how can we say it mathematically, ma'am?
Okay. So I don't know if it is going a little off track, but I hope students are following. We'll quickly, after this particular question, maybe we'll start with the problem solving session. Okay, so your question is, in saturation region, Ohm's law is not followed, right? So let's take up our output characteristics for MOSFET.
MOSFET.
Okay, so how does your output characteristics look like? It first
Yes.
rises, then it stabilizes. And
Yes,
when
ma'am.
it stabilizes, we call it as saturation region. Now,
Yes,
what
ma'am.
does Ohm's law say? V equal to IR,
IR.
or R equal to V by I, right?
Yes, ma'am.
But when you look at this particular region, ideally, it should be constant. That means R will always be constant with the increasing, R will be actually reducing with increasing V, because so okay, this is V versus I, right? So
Relation between
saturation.
V and I.
So here actually when we talk in MOSFET, we don't talk about R, we generally talk about G, the conductance, because it is I versus V graph, right? So G will be I by V.
Yeah, differentiation of ID versus VG.
ID versus VDS. So here, if you observe carefully, so in this particular region, it was increasing linearly. So it behaves as a resistive, it has a resistive behavior, right?
Yes, ma'am.
V and I are proportional to each other. But in this region, it actually saturates. So now there is no link between V and I. They have become independent.
Yes, ma'am. That was yeah.
This independency basically is referred to as like non-following of Ohm's law, because Ohm's law means a direct dependence between I and V. But here there is a independency that comes into picture due to the saturation condition. So that's why it does not follow the Ohm's law. So that is the idea.
Yes. Mathematically, can we say anything? Means, if it is actually here
okay,
also.
Mathematically, I'll tell you. ID sat, when we talk about ID sat in a MOSFET, it's
the drain current equation will get changed, ma'am. 1/2.
Yes, current equation will change, and it's K by 2 VGS minus VTH whole square. Now, if you see, according to this particular graph, always your equation should be a function. So I should be a function of VDS, right? But when you get the saturation, it's actually independent of VDS. So
yes, ma'am.
This independency is actually like there is no relation between I and V, right? So makes it as it does not follow an Ohm's law. So that's why it's
yes, super. Thank you, ma'am.
Yeah. Chandan, you have raised your hand. Is there a question?
Yes, ma'am. Why is biasing always DC? Why can't it be AC, ma'am?
Why is bias always DC? Why not AC? Okay. So, first of all, let us consider any of these one of the two. Okay, any graph, like let's say input let's consider the transfer function graph. So transfer function graph may, if you put, let's say you fix your bias here, or you fix your bias over here, Q1 and Q2, right? For these both points, you will get different electrical behavior. Like your currents will be different, and your corresponding, the amount of VDS you will require to attain a certain amount of current you want will be very different, right? Each and every point with a slight change in your point will actually change your electrical behavior. Do you understand that? Chandan, are you there?
Yes, ma'am. Yes, ma'am.
You understand that the moment your Q point shifts very slightly, your current will definitely change, your electrical behavior will definitely change,
Yes, ma'am.
right? Now let's say if you are biasing using an AC signal, then what happens? Your Q point is not actually a fixed point, rather it is changing continuously and both in positive as well as negative direction. Now when that type of change is there, when your Q point is fluctuating all the way from positive to negative, for each and every sampling point, like let's say I'm taking my times in few picoseconds, okay? So at each and every point, I want to amplify my signal. तो क्या होगा at each and every point, since your Q point is changing, your amplification factor corresponding to that will definitely change. So it will basically introduce a distortion which will be uncontrollable and which won't be in your hand to actually predict, okay, what type of distortion is coming and how to actually deal with that distortion. If you apply AC voltage at your bias, am I making
Yes, ma'am, I
sense? Are
understand.
you getting it?
Yes, ma'am.
So that's why it is very important to fix a bias point. That's why biasing is always done using DC. Yeah. Okay. Is there anything else? So I have touched upon, I guess, a few basics, and meanwhile, each and every week, corresponding to that week, we'll talk about few more basics, and then we'll start the session. But out and out, I have touched upon at least some introduction to motivate this subject and to motivate this particular session. So with this, now let's move on to our problem. So considering this first problem, so in this problem you have to find the I1 which is flowing through 3 kilo ohm for this particular given circuit. So by looking at this circuit and considering that you have to find the current, how will you find the current? What is it that comes to your mind? That the first approach that you will use to get the current?
Mesh analysis.
Mesh analysis. So even in electronics, you will use KCL and KVL as your major theorems. So here also for circuits, we will use KCLs and KVL. With KCL and KVL, rather than having resistors, we will have maybe BJTs. So we'll use BJT equations corresponding to them or MOSFET equations corresponding to them. But the basics of any circuit is always same, be it an electrical circuit or an electronic circuit. KCL and KVL should always satisfy. Is this clear?
Clear.
Okay. So now with this, let's solve this problem. So we have to find this current I1, right? So first of all, there are a lot of ways to which people take conventions for their KVL and KCL, and all of them are correct. All the conventions are correct. Just that you should not mix and merge the two, because each and every person has their own convention, and if you mix two of them, you will definitely get confused and end up getting wrong results. Okay, so you have to have a convention of your own. Now here maybe I'll show you what my convention is. You can solve it using your own convention, but just don't get confused and don't mix two or three conventions together. Okay, just follow one single convention. So what I'll do, I'll apply KCL, let's say at node V1, V2 and V3. Okay, KCL at V1. So what my convention is that I consider V1 at as a high voltage node. that particular node as a high voltage node, and I consider all the currents coming out of that node. So when I'm writing my currents, I'll write it as V1 minus V3 by 3 kilo ohms, V1 minus 15 by 2 kilo ohms, plus V1 minus V2 by 14 kilo ohms. This is zero. So this is the convention that I follow. You can follow your own convention. Okay. Now KCL at V2. So at V2 we have V2 minus 1 2 kilo ohms, V2 minus V1 by 14 kilo ohms, plus V2 minus V3. So if you observe,
Excuse me, ma'am.
sorry, yes, go ahead.
Ma'am, could you please explain why we are using here both KVL and KCL?
Sorry.
Ma'am, I asked that why are we using both KCL and KVL over here?
We are only using KCL, right? I'm writing current equations only, right?
Okay, I just misunderstood.
This is only KCL because I'm only writing current equations.
Okay, miss.
For KVL, you'll use voltage equation. Now, similarly, at KCL for V3, we'll have V3 minus 1 by 2 kilo ohms, V3 minus V2 plus V3 minus V1 by 14 kilo ohms equal to 0. So by solving these three equations, so see, we have V1, V2, V3. We have three variables and we have three equations. So we can easily solve them. So after solving these three equations, we will get the values for V1, V2, V3. Now when we want I1, so I1 should be V3 minus V1 upon 3 kilo ohms. This is actually the I1. So once we solve the KCL, all three KCLs simultaneously, we will get the values for V1, V2 and V3. You can solve these equations, right?
Ma'am, it will be V3 minus
madam.
V1 upon 3
Yes.
at node 3.
Yes, V3 minus V1 upon, okay, so this 14, okay, yeah, this is not 14, this is 3. Yes, this is 3, right? Thank you. So what we have to do is, we have to solve these three equations simultaneously, and then we'll get V1, V2, V3. So everyone, can we solve these equations? Like, can you solve these equations? You can solve them, right?
Yes, ma'am.
Yes, ma'am.
Yeah. So I'll quickly write down the values of V1, V2, V3. I've already solved them. It's 10 volts, 3 volts, and 4 volts. Okay. So these are the values of V1, V2, and V3. So now we want I1. So I1 is V3 minus V1 by 3K. That is 4 minus 10 by 3K. That is minus 2 milliampere.
2 milliampere, yes.
Okay. So first question, what does negative current mean?
Opposite direction.
Opposite direction.
Yeah.
Flowing against I1.
Flowing against I1. So actually the I1 which has been mentioned here is incorrect. So the flow of current will be like this. This is
Source
opposite
current,
to
ma'am.
I1.
You can say that source current, ma'am. It is incoming, not outgoing.
Sorry, I didn't get it.
Current direction, if it is going to node it is plus, if it is coming to the source it is negative number.
See,
But here
those
all
are
the three are
your,
sources, I think.
yeah, and it's your convention how you take it. And if we look at it from a layman's perspective also, it is very evident that 15 volt is the highest source voltage that we have. It's the biggest source voltage. So it's definite that the majority current coming out or flowing in the circuit will be from this particular source. So it makes sense when the current direction is from this larger source to the source of 1 volt. So that is also evident. So even without solving this also, we could have commented on the direction of I1. But here numerically also we have got the thing that is the current direction will be opposite to I1. Okay. Now let's quickly move to the next problem. In the same circuit, we have to find V12 voltage across 14 kilo ohm resistor. V12. So we know V1, we know V2. So what will be the V12?
7 volt.
7. V1 minus V2 is V12. So this is 10 minus 3 volts, I guess. Right? Yeah, 10 minus 3 volts, that is 7. Option. Now coming to this next problem. Okay, so for this circuit, we have to find the DC voltage at its output node, which is this. This is Vout. So at this particular node, you have to find what is the voltage with this node to ground, and you have to find DC voltage. So when it is pressing and saying that you have to find the DC voltage, so what will happen to this circuit if it is only a DC voltage? So DC voltage means
Capacitors are open, I guess.
yes,
Open
capacitors are open circuit. So for DC, capacitors are open. For AC, considering if there is no restriction
Short
on,
circuit.
yeah, there is no
Capacitors are short
restriction
circuit.
on frequencies, then we consider capacitor as short circuit.
Short circuit.
Yes, and this will be open circuit. So this is 0. Now this has open circuit. Do we have another
It's
capacitor?
open.
Yeah, this is also open circuit, right? So the moment this is an open circuit, now how will your actual circuit look like? So it's
500 in series with 50 and another 50. Only these three resistors will be existing.
yes. So it is 500, 50,
And another 51.
50.
That's
And
it.
this is your Vout. So this is the only circuit that you will see. So when we want to find Vout, which is actually this voltage. So how will we find? It is
Potential divider rule.
yes, potential, simple potential divider rule. So Vout will be VDD into 100 upon 600. 12 into 100 by 600. So Vout is 2 volts, right? Any doubts in this? These are very simple, right? So I don't think anyone has any doubts. If just in case you have any doubts, please raise your doubts, okay? So let's quickly move to the next problem. So in this problem, you have to use the same circuit. You can simply unmute and ask. Fine. You can. You don't have to raise your hand and wait for me to respond. You can simply unmute yourself. And
Ma'am, answer to second question, ma'am.
sorry.
Second question.
Second question.
Once.
Acha, second question. Yeah.
Yes, ma'am.
It was just to find V12.
Okay.
It
Okay,
was
ma'am.
just to find V12. Yes.
Okay.
Yeah. yeah, for in the same circuit. Now this said that assuming the capacitors are shorted for the input signal frequency, we have to calculate the output signal. Now one more thing, when it is said like what will be the output signal, when we talk about signals, it's mostly we are talking about AC signal. So the AC that you give, what is the corresponding AC output? So signal is corresponding to your AC, whereas when it says output voltage or output current, it mostly corresponds to DC analysis or DC values. Whereas when it is said like what is the signal amount or output signal, so that signal word is used for AC. So just keep that in mind, because sometimes this clarity is missing. So we need to have this understanding that signal is for AC, and when it says like output voltage, output current, you can go with DC. Okay, and since you do have options, so you can look into the options, and from there also you can judge, because the larger values will definitely be for DC, and when the values are very small, it is mostly AC. So from there also you can judge. But yeah, signals is for AC, so keep that in mind. So here it has already been mentioned that your capacitors have been shorted, and now you have to find the output signal. So output signal for this corresponding input signal, which is 80 sine omega t. So now since this is shorted, how will your circuit look like? It is 50, 500, and since we are considering AC analysis, so let's put all the DC sources to ground, because we only want to see the effects of AC signals, right? So here let's put this VDD to virtual ground, or we call it AC ground. Then we have 50, then it is shorted, and then it is ground. From here we have to find VR for this CP. We have shorted this and we have put this to ground. CP is sine omega t. Yes, and this is in millivolts. So you have to find the voltage across this. So now if you look at this circuit carefully, it is like 50 ohm and 50 ohm in series with the parallel combination of 550, right? So the actual circuit turns out to be like this. This is how your circuit turns out. So total R total will look like this. Now you have to find your voltage V out corresponding to this parallel combination. So can you quickly solve it? This is simple voltage divider, right?
$95.45.
How much?
95.45.
95.45. How you are getting 95 when your input is 80?
No, R total I thought you were asking.
No, R total nahi. I'm asking
Yeah,
about
okay,
V
okay.
out.
38
1.90,
millivolt.
ma'am.
38 millivolt.
38 millivolt. The answer will be 38 millivolt. So how will you find it? So it is like V out is 50 parallel 500 by 50 plus 50 parallel 500 into 80 millivolts. So V out is 38 millivolts.
Excuse me, ma'am.
Yes.
Ma'am, why was VDD shorted?
Yeah, so what I said is we basically want only the effect
Signal,
of
it's
signal.
AC, and D.
Yes.
Short.
We only want the effect of signal, that is AC signal, AC input.
AC.
We want the effect of AC input at the output node. So that's why we made sure that there is no DC, like we are not seeing the effect of DC, we are only seeing the effect of AC. That's why I shorted the 5 volts and I made the 12 volts to ground. So I can only see the effect of AC signal.
Okay, ma'am.
Okay.
Yes, I have another question, please. Yes, I understand that we have shorted the DC because the signal of interest is the AC.
Yes.
But really, I don't know why we shorted the capacitor.
So see, here first of all, it's mentioned in the question.
Simply the condition.
Assume the capacitor.
Simply the condition.
Yes, it is actually mentioned that for the given frequency, your capacitor acts as a short circuit. And that's why I never said that for all the AC analysis, your capacitor will be shorted because it completely depends on your frequency. But if it is like a simple type of analysis, we can safely take capacitor to be shorted. Otherwise, we have to consider the Z, that is impedance of the capacitor if it is frequency dependent circuit. And we have to consider the effect of frequency. But here in the question,
XC has to be considered.
Yes, XC has to be considered. But here in the question, it was directly mentioned that assume your capacitors to be shorted.
Assume capacitor shorted.
Yes, I got it. Thank you so much.
Yeah. So let's move on to the next problem. Now here, after passive components, we have come to after going through all basic components, that is RLC, we have come to an electronic component, which is also passive. And today we will be only dealing with passive components, like we will have a diode-based questions and resistor capacitor-based questions only. Maybe from next session we'll have MOSFET-based questions. So yeah, in this particular question, we have V0 to be 2.2 volts, 2.02 volts. We have R as 0.9 kilo ohms. And the diode follows the equation ID equal to IS exponential Vd by dt, where Is is given to be 2.4 into 10 to the power minus 16. It is milliamperes. And Vt is 26 millivolts at room temperature. Now we have to find the value of ID and we have to report it in milliamperes. So we have to solve this problem. Now if we look at this equation of ID, we have Is, we have Vt, we don't know about Vd. So first of all, what is Vd?
We need to consider that to be 0.68, or else iteratively we'll have to find it.
So it is basically the voltage drop that appears across the diode once it is turned on. Okay. So Vt is the voltage that appears across the diode, and it is the drop across the diode that appears when the diode is turned on. Okay. So here, since Vd is not given, so let's assume a value. Typically, for a silicon diode, your Vd is 0.65 to 0.7 volts. It is in the range of 0.65 to 0.7 volts. So let us consider any value. I am considering 0.65 volts for my calculation. You can take some other value, but try to be relatively in the range. So that is from 0.65 to 0.7 volts. Okay. So assume Vd to be 0.65 volts. Now if the Vd is 0.65 volts, so let's first calculate the ID. How much is the ID that we are getting if our Vd is 0.65? So how much is the ID that we are getting from this?
17.28 microampere.
17.28 microampere. Now, if you observe carefully, so let's say I've said that VD is 0.65 volts, right? So it is the drop across the diode. So the remaining voltage out of 2.02 volts will drop across the resistor. So the voltage across resistor will be 2.02 minus 0.65 volts, right? So which is 1.37 volts. And the current across the diode will be 1.37 by 0.9 milliampere. So IR is actually 1.5 milliampere, right? So if you see, first of all, there is a lot of discrepancy in ID and IR. Can you see that? There is a discrepancy. Here we are getting 17.28 micro and here we are getting 1.5 milli. But if you observe carefully, these two components are in series. So when the components are in series, that means a single
Current should be same.
Yes, the current should be same. So that means there is some issue with the assumptions that we have taken. So now what we will do, since we have the current across resistor, let's consider this current to be equal to the diode current. Okay. This should be precise 1.52. Yeah. So let's consider this as our current. Okay. Diode current. Now when we have the diode current, from here we can find VD. So let's say I'll call it as equation 1. Now we are going for equation 2. So with this current, we'll find the value of VD. So VD is VT ln ID by IS, right? So we'll simply substitute our value ln 1.52 by 2.4 into 10⁻⁻⁻. So you can solve this equation and you'll find the value of VD as 0.946 volts. Okay, you'll find the value of VD as 0.946. Now considering this as our VD, let's again solve the same equations. Okay, now for this particular VD, our VR is 1.074 volts. The corresponding IR is 1.1933 milliampere. Now again considering this as ID of 1.1933 milliampere, when we again calculate VD, it turns out to be 0.9397 volts. So here if you see our VD, which we considered or which we assume, and the VD that we are getting right now are a little far away from each other. They are not coinciding, right? So we have to go for another iteration. The same way, we have to just add another iteration, and if you observe very carefully, you can find that first we assumed it to be 0.65, then we got 0.946, but now we have got 0.9397, which is very close by. So it shows that in the next iteration we might get our result. So in this iteration, just simply consider 0.9397 0.97 volts as our VD. With this VD, we'll get VR to be 1.08 volts. IR is 1.2 milliampere, which is equal to ID. Now, with this value of ID, let us all calculate VD, which is VTLN 1.2 0.4. Now, all of you take out your calculators and quickly calculate the value of VD and let me know.
Coming as 0.939, I guess.
Aisha?
Yes.
Don't we need any other iteration?
No, it is coinciding. 0.939 up to 3 digit.
Yes. So up to 3 digits, we have got it as 0.939, and which was actually coinciding with the assumption that we already made. That means now it is self-sustained. And if you can, now what you can do, you can calculate with this value, you can see that ID, IR, everything comes into place. So it also follows that in series only single value of current in play. So all electrical rules are being satisfied. With that, we have got a self-sustained loop. So after this, you don't need further iterations. So this is the final answer. So what is the value of your ID? It is 1.2 milliampere. So the final answer is 1.2 milliampere. But see, what would have happened in the first iteration when you calculated ID, you have got 17.228 microamperes, and when you go to your options, you don't find 17.28 microamperes, and you are like, where is it going on? So the first thing that we do, we never question ourselves, we question the person in front of us. So we simply doubt on the problem, that there is something wrong with the problem, but actually it's not the case. Got it? So it was somebody's question, right? Somebody said that the person was not getting the options in the problem. The reason is, actually it was not a problem which was going to be solved with just single iteration. It would take multiple iterations. There are problems like that, where you have to use multiple iterations to get your correct answer. So is this clear?
What is first order approximation?
First order approximation, where is it coming from?
In the question, it is mentioned, do not use the first order approximation. What it may be, the question is.
Oh, okay. So here it says like solve the problem iteratively, numerically. Do not use the first order approximation. First order approximation.
It may mean about the iteration we are
Yeah,
using.
I guess it is just that you have to go through that multiple iterations. That is one thing. And secondly, first order, because when we say first order approximation, there are different things that comes into your mind. First order, because sometimes we change exponentials also to like first order. So it's like, yeah, diode equation, depending on diode equation also, we change like exponential to linear form, considering like all the higher orders to be zero. So that is also there. So yeah, but I'm not really like 100% sure what they are trying to say here. But most probably it's just that you have to use the equation which is given, and secondly you have to use this iterative method for consistent solution.
Okay, thank you.
Yes. Any questions? So maybe we'll move to next question. So in this problem again, so here the cut-in voltage is already given. So cut-in voltage is basically VD. VD is already given. VD has 0.65 volts. We have 2.02 volts as VDD. R is 0.9 kilo ohm. And we have to find the value of current ID. We have to simply find the value of ID. So now here it is not mentioned that you have to go through an iterative method, and also we don't have to go through an iterative method. Why? Because VD is already given and VT is already known. So almost everything is already known. So let's say if VT is not known, so that also you can solve this problem. That is simply we know that IR equal to ID. We'll use this concept.
It's 1.52.
So
the
yeah,
answer.
so by using this concept, we'll first find IR, then we'll go to, like, we'll say IR equal to ID and we'll get it, and which is actually 1.52, because IR is 1.37, right? 1.37 by 0.9 milliamperes, which comes out to be 1.52 milliamperes. Any doubts in this? I don't think any doubts is there, right?
It's clear. It's
Just
easy.
in case if anyone has any doubt, feel free to ask. See, somebody might catch it very early, but somebody, if you have doubts, it's better to clear here rather than making a mistake in exam, right? Nobody is here to judge you.
Why are we equating IR equals to ID, ma'am?
Sorry. Why we are getting
Series
IR equal to
diode
ID?
and resistors.
Yeah.
Resistor is in series, and in series the current flowing will be same.
So the basic electrical concept
Okay.
is in
Yes, ma'am.
parallel voltages are equal, means the current is always equal.
Okay, okay, got it.
That's a simple rule. We are saying that current in a straight line or in a series, the current, a single current can flow through all the components. So by that principle, we are simply writing IR equal to ID. Yeah?
How did we get 1.37?
How did we get 1.37? Okay,
Yes.
so we are getting IR as VDD minus VD by R. So it is 2.02 minus 0.65 by 0.9.
Divided by 0.9. Okay, like kilo later on. Absolutely.
So from here the kilo becomes milli, and you'll simply subtract, so you'll get this.
1.2222. It's 1.52.
Clear?
Yes, ma'am. Thank you.
So maybe we will move to the next problem. So in this problem, for the given circuit with a cutoff voltage of 0.7.
Madam, for this problem, can we go very slowly? This is really screwing. Like trying to solve this since many days, but
Okay,
please.
this particular problem. Okay.
Let's go very slowly for this one. Yeah, please.
So here we have VD, which is 0.7 volts. We have Vx as 7 volts. 7 volts, 0.7 volts. Yeah. R1 is 0.1 volts and R2 is 2.1 volts. Right? Now what is the current to R2? And we have to get the resolution millivolts. So first of all, here it is 0.7 volts. So what is the first thing that comes to our mind, seeing that at this
It is conducting. It's conducting.
Diode is
and diode is on.
So first
current will be flowing through that one.
Assume.
So ma'am, if we first assume open circuit.
No. It's closed. Why? Because Vx to the anode, it's 7 volts and it's beyond the cut-in voltage.
It's not short circuit.
It's definitely, it's conducting. It's conducting.
It's conducting.
Yes.
Diode is conducting.
Diode is conducting. So in that case, we will be like, so this is, okay, maybe zoom it. So this is ID, this is ID, this is I1, this is I2. From simple KCL, we can see that I2 is ID plus I1.
ID plus I1, absolutely.
Right? So, okay. Now, here we have 0.7 volts. So, how does that 7.7 volt appear here? Is like 7. So across R1, the voltage that we have is 0.7 volts, right? So from this image, if we observe very carefully, the voltage across R1 is 0.7 volts. And since the circuit has a supply of 7 volts, that means the remaining voltage will drop across R2, right? So VR2 is 6.3. Is this clear to everyone? Any doubts in that?
G, once again, like repeat it, please.
So
This circuit?
yeah. Is this circuit clear, like how this 0.7 volt has appeared and how we have placed the potentials like plus and minus?
Absolutely.
This is clear, right? And 0.7 volt is coming from diode. But if you
Diode
observe,
cut-in voltage?
yes, diode cut-in voltage. But if you observe very carefully, this 0.7 volt is actually in parallel with R1.
Parallel with R1, so voltages are
The
same.
voltages are same. So actually the voltages across R1 are also 0.7 volts, right? But this whole circuit has a supply of 7 volts.
7 volts.
So that means the 7 volts will drop across this
0.7 over here
as well
and the
as
remaining 6.3 across R2. Thank you. Absolutely.
Right? So now this is clear. So we know our R1, V1, V2, R1, like VR1, VR2 is clear to us. So since we know VR1, VR2, we also know that R2 is 2.1 kilo ohms and R1 is 0.1 kilo ohms. So what we can do, we can find IR1 and IR2, right? We can do that.
Yes.
So
current division rule?
Simply we can use Ohm's law.
Okay.
Voltages we know, we'll simply use
resistance we have.
Yeah. Okay. So we'll get the currents. So what are the currents that we are getting? It is 7 milliamps and this one is
3 milliampere.
3 milliamps. Now we know that ID plus I1 or IR1 equal to IR2, right? So ID is IR2 minus IR1. So IR2 is how much? 3 milliampere minus 7 milliampere. So ID is minus 4 milliampere. What was the direction of current? ID was like this, right? But when it says ID is minus 4, that means the direction has been inverted, right?
Yes.
Minus 4. But, okay, very important. Everyone please pay attention over here. Earlier the diode current direction was ID1. After solving, we have got it as ID2. My question is ID2 possible?
No, ma'am.
No.
Is ID2 possible? Everyone?
Because it will be in
anode, no.
the reverse bias.
Diode is a unidirectional device. It can transmit
no current from
only in
cathode to
one-
anode.
Yes, it can transmit only in one direction, or it can conduct only in one direction. So ID2 is not possible at all. That means this is wrong that means our assumption is actually wrong. So the very first assumption that we made, that the diode is on, that assumption itself is wrong. Getting my point?
Yes.
How we have concluded that the assumption is wrong? Is it clear to everyone?
Ma'am,
Yes.
can I ask you?
Yes.
Now this diode is conducted in forward direction when it is biased.
Yes.
Correct? It will conduct in one direction only.
Yes.
Now suppose it is not conducting.
Yes.
That means the R1 and R2 will be added. If it's not conducting, it's a closed circuit, open circuit.
Yes.
Correct?
Yes.
So 7 volts upon R1 plus R2 is the current flowing to the R2.
Yes.
Yeah, because it's a series circuit. Correct?
Yes. Yes.
The moment this diode comes in a picture, right, which is parallel to the R1,
yes.
In that case, the current will be divided.
Yeah.
Current will be divided. It's a parallel circuit.
Yeah, that's what we are talking about here, right? So first of all, we considered that diode is on.
Diode is on.
And we got a completely wrong result, which is not possible at all, which is against the laws of electrical and electronics.
Yes.
So simply that shows that our assumption is wrong.
Okay, now
now we will go for next assumption, that is diode is off. And with this assumption, we'll get 7 volts in parallel, like in series with R1 and R2 with 0.1 kilo ohm, 2.1 kilo ohm, and what was our current across? Current through R2.
That's the same current will come.
The same series current. So that is 7 by 2.1 plus 0.1. So
2.2, yeah.
Equal to 7 by 2.2 milliamps. So where I is 3.18 milliamps. So is this clear to everyone?
Yes.
Yes.
See, so you should always consider, every time here, the moment you look into the circuit, you feel like, okay, 7 volts laga hua hai at the positive terminal of your PN junction, and it is almost grounded to your negative terminal of your PN junction. It appears as if your diode is forward biased, and it's obvious to appear that way. But when you are numerically solving, it turns out that that's not the case, and it completely changes your vision. So that's why sometimes the things are not as obvious as they appear. So here it was very obvious saying that, oh, diode is forward biased, you need not to solve further. But actually that was a wrong assumption. So we have to be very careful, and we need to, so for all these things to cut off or to contradict your own assumptions, your fundamentals need to be very clear. Now, in place of a diode, if there was a resistor, I didn't have any problem with that, right? I don't have any problem. If there was a resistor, a negative current doesn't make any problem. Even there was a capacitor or an inductor, it doesn't cause any problem. It was just because there was a diode, and the principle of diode says that it is a unidirectional device, it creates this new problem. And it is very important to understand this. And for this, you have to be very vigilant, and your presence of mind needs to work here, that, are we really doing it right? Is this clear to everyone? How we came to the conclusion that diode is actually off rather than being on?
Yes, ma'am.
Ma'am, can I ask you something?
Yes, please go ahead.
Madam, this IR1 you have calculated, which is 0.7 volts, which is the drop across the diode, divided by 0.1, correct?
Yes.
How the 0.1 has come in the picture, ma'am?
That is resistor value, right? The
resistor value of the diode.
No. R1 ka value.
No, resistance R1 value is already given.
In question, it is mentioned.
Okay. R1
is mentioned in the question.
Yeah. 0.1.
Underlined with the red, you can see that. Vx is 7 volts,
R1
R1 and R2, respectively. Yeah.
Okay.
So
Okay.
hope this is clear. Now let's move on to the next problem quickly.
Ma'am,
Yes. Go ahead.
ma'am, how can we identify whether a diode is in on or off? Because 0.7 volt is nothing but
ये
the diode
दिमाग
starts
में भी है
conducting.
जी
Yeah, so that was the catch in this particular question. Like generally, how do you consider a diode is on or off? So you
Ma'am, if
simply
it
see
is
the
greater
anode
than
is at higher
0.7
potential,
volt,
so
yeah.
we thought
then
Sorry.
yeah.
There is an overlap. Actually, I'm unable to see who is talking. So yeah, please go ahead.
Ma'am, here the cut-in voltage is given as 0.7, which means that the diode starts conducting after this particular voltage, which means that the diode is conducting. No, why we are taking is in off condition.
What made the diode to be reverse biased? That is the straightaway question under this
Okay.
condition. So if that could be answered, it would be really helpful.
Okay.
Is there any method or way to identify by seeing the circuit itself whether a diode is conducting or not?
So
I
that
mean,
is what
which
we did
the
in the
diode is
first
on or
place.
off.
See, that is what we did in the first place, right? When we assumed that diode is on, so what was the basis for considering that diode being on? The basis was that,
Actually, in this question, that voltage across diode is not crossing 0.7. That's why it is not getting turned on. Why in the second calculation, we get
and
it as 0.33,
also
0.32
you
around.
can think of it like the resistor R2 is way bigger than resistor R1. It is 2.1 to 0.1. So which basically shows that the majority voltage is being dropped across your R2 rather than appearing across R1 or across the diode, which basically causes the issue. Am I audible? Hello?
Yes, ma'am.
Yes, ma'am, you are
Okay,
audible.
so
Yeah,
because
absolutely, we can
at
hear
my
you.
screen I can see that you lost your network connection, so I'm really not sure. Is my screen visible? Hello? Hello? Oh. Hello? Hello? Am I audible?
Ji, we can hear
Yeah.
you
I
now.
got
Yes, ma'am.
disconnected, right? Yeah, network problems. So, what I was saying is, how did this happen? What might be the physics behind this? So, one thing that we can observe very carefully is your resistor values. So, 2.1 volts is your R2, whereas only 0.1 kilo ohms is your R1. So, because of this ratio, if you can think of like the voltage drop across these resistors, so you can see that the majority voltage will drop across R2. So, what might have
Which is
happened?
given to
Yes,
which
so
is given to the cathode.
so what might have happened is actually that 0.7 volt, which was which should have appeared across your diode, it is not able to receive that much voltage, which is making it to go into the cutoff state, and that's why the diode is turned off. But it was not clearly evident from the circuit. But mathematical calculations actually showed you that. And even if you do an experiment, you can find it out that that works the same way. Yeah. So sometimes few things are not as straightforward as they appear. But sometimes, yeah, there are many questions which are very straightforward, that like the second question, you simply had to find V12, right? So that is not a rocket science. V12 means V1 minus V2. So it is as straightforward as that. But in this particular question, it appears that the diode is on, but actually it is not on. So yeah, we have to be a little vigilant sometimes, and also we need to have the presence of mind. Like here, in place of resistor, if there was a capacitor, like in place of diode, if there was a capacitor or an resistor, there would not have been any problem. We would have gone forward with the solution that we got. But since there was a diode, the problem arises. So that presence of mind needs to be there. So hope this is clear. Should we move?
Also,
yes.
If the direction of diode was opposite,
yeah,
then our assumption would have been right.
If the direction was opposite, then okay, so if the direction was opposite, then first thing you would have taken the direction of current also opposite. Now here, why we said like ID plus I1 equal to I2 is because considering the direction of current of diode. Now if I am saying my diode is opposite, then it would have appeared like
it's a reverse biased.
Yeah, it is reverse biased, and the direction of current will already be like this. ID will be like this, I1 will be like this.
Yes.
And maybe we'll consider I2 like this, so to satisfy your KCL, and we would have written like I2 plus I1 equal to ID, somewhat like this. The equation would have changed. It is all depending on your conventions and considering that the current of diode is unidirectional and all that. So yeah.
Ma'am, in equation, ID is I is equal to IS into e raised to that VD by VT.
Yes.
IS is very small value.
Yes, it is always a small value.
Very small value. And then we calculate, just for my information, ma'am, when we calculate e raised to that VD by VT.
Yes.
That is the voltage, check-in voltage and drive-in voltage, whatever we call it, by VT. So it is that figure itself comes in the terms of some figure into 10 raised to 12 or 10 raised to 10, 11.
Yes.
So they cancels out most of the time.
Yes.
But at times, it gives some funny results, which I am not able to able to tell you, ma'am, because the numbers normally it is in milliamps. Supposed to be in milliamps. The ID has to be in milliamps, correct, ma'am?
So okay, so there might be a condition when your exponential can go drastically and you might burn your diode. That also happens because this is an exponential equation.
Yes.
And ideally the equation is Is exponential V by Vt, where V corresponds to the voltage that you are applying. And the value of applying voltage, so let's say if you apply 5 volts to your diode, so the exponential factor for 5 by 0.026 will be huge, and the currents will like exceed, and they are come in amperes, and it will simply burn your diode. That happens.
Okay. Now in a earlier earlier lecture, ma'am, we have that -1 coming in a picture. Is it for the ideal diode or what it is?
-1, I didn't get it.
I mean that
Okay. ID equal to Is exponential
e raised to
V minus Vt minus 1. So this is actually the we call it the diode equation. This is the diode equation, actual diode equation. But to simplify it further, we simply remove this 1, considering that this exponential is much larger than 1.
Okay.
And we simply say like ID is Is exponential V by Vt.
Okay, so it has nothing to do with the ideal diode or non-standard diode.
No.
In fact, the one has no value in compared to that. I mean,
because exponential is exponential, right?
To 12,
so now when this 1 comes into picture, like when your exponential, this factor is much less than 1. At that case, like you will see these things, like it's in negative exponentials. So it will be smaller value, less than 1. In that case, you will see those things, like 1 coming into picture. But actually, since we apply higher voltages, so exponential term always dominates. So 1 is like 1 never comes into picture. So yeah.
Okay.
Because if like for example exponential of 1 is still 2 point something, right, e to the power 1, 2.7, so which is also 2 times of 1.
Yes.
So any factor, any voltage that you will apply which will be much higher than your VT, that is 0.026 millivolts, you will always apply your voltage beyond your cut-in voltage, which is 0.7 volts, to conduct your diode. So that exponential always dominates. That's why we eliminate this one. That is the only idea behind it, to simplify the calculations. Hope this is clear.
Yeah, ma'am. Thank you.
Yeah.
No, actually, exponential of V by eta VT, no.
Eta, yeah. So there is another factor, eta, which is known as ideality factor. It changes depending on. It changes with silicon, germanium, like depending on what material you are using. So it's a material dependent factor.
I use the silicon, no, then it will be 2.
But for simplicity, sometimes eta is given. So see, it all depends on what actually is asked out of your question. If question provides you with maximum information, you try to use all of that information. But if the informations are missing, so rather than going for assumptions and getting your results wrong, we should go with something which is more generalized and so we should try to look into the given as well as what is being asked. In given, if in this problem eta value was mentioned, then I would have definitely used that eta value, right? But earlier in the very beginning, the first problem that we saw, there the formula was already given. So when the formula is already mentioned in the problem, you don't have to think twice. You can just simply apply that formula. Okay? But it's sometimes like if the values are given and you can find maximum values, then you can use them. If it is not mentioned, you can simply ignore them. So it ultimately depends on what is being asked. What is being asked and what is actually being expected out of you from that particular question. So it depends on that.
Okay.
Yeah. So let's quickly move on to next problem. So it's already 8. Do you want me to continue further? We have like 3-4 questions more. Yeah, 4 questions more.
Madam, it would be helpful, please.
Okay.
Others?
So maybe we can, so let's quickly finish them off and then I'll upload the video, and just in case if you have doubts, you can stay back or we can discuss in the next session. Or if you want, we can take up these problems in next session as if like whatever.
That would be better. Let's not go in hurry. What other says? Please.
Yeah, we can go for other session, no problem.
So next week?
Yeah, let's not go in hurry. We'll go very clearly as just we have done. Madam, please, a humble request.
Okay, so maybe I'll take up these next 4 questions which I already prepared in the next coming week. Tomorrow the other TA will be here. So if he if he can consider these questions, then will also do. But I won't be very sure, like, because we are like working independently. So I'm really not sure what are his set of questions.
Let's do it now.
So do you want me to go through these problems now, or do you want me to take up this next Monday? So first we'll start with these problems, then we'll go to the next week problems.
Okay, ma'am.
No, yeah, we'll have to submit the we'll have to submit the assignment, right?
Yeah.
I guess the deadline is till 9th.
9.
Yes, ma'am.
9. We'll have to submit by then.
Yeah, and the next session.
2 assignments has come up.
Okay.
And 2 assignments has come up.
Okay, yeah. So, or maybe what you can do is, I guess tomorrow the next TA might come up with these questions and he might actually solve these. Yeah, only 4 questions. Only 4 questions are remaining. So, do you want me to quickly solve them, or should I provide you with the solutions? You can just go through the solutions, and just in case of any doubt, you may raise them in like next session or in the YouTube comments. Is it okay?
Yes, I have just one request.
Where can we get that solution?
Sorry.
I just have one request, that serial diode problem, right? In which two diodes are in series, and if I understand correctly, it results in two exponential equations. So I tried to find out some ways of solving that, but any tips you would have to because the ID is the ID will be the VD will appear both as a variable as well as in the exponential, and there are two VDs, V diode 1 and V diode 2. There's a problem.
Okay, so the thing is
that problem I would like to just see.
But now the thing is we have 4 problems left. So do you want me to take these problems or just clear your doubts and leave these problems for next week? I want audience opinion depending on that.
We will solve it, madam.
But better to solve it, where to submit the...
We'll solve it.
Okay,
let's finish
so can you hold your question? Maybe we can discuss next time, because this time we are already overboard by 8 minutes. Okay, so if it is not very urgent, maybe we can take it up next week, and meanwhile I'll quickly solve these 4 questions, or I'll give you some hints so you can solve your assignments. Okay, so in this particular question, consider a non-ideal diode with the ID of ID is already mentioned to be 1.7 milliamperes, and VD, the change in VD, that is delta VD, is given to be 2 millivolts. What is the change in ID? You have to find delta ID and give your answers in micro. It is also given like VT is 0.026 volts or 26 millivolts. So this is given. So first of all, VD, delta VD is given. What you actually want is delta VD by delta ID, delta ID by delta VD, or DID by DVD. Okay. So differential equation. So basically you have to use the differential equation, and when you differentiate this particular equation, what you will get is into VD by VT, right? So DID by DVD, you simply substitute ID, this is ID, simply substitute your ID into VD. VD is actually your delta VD. So यहाँ पे you can substitute your 2 millivolt by 26 millivolts. So DID that you get, that is delta ID that you get, is 130.77 microamps. So this one. Okay. So when it is asked about change, most of the times it is differentiation. You differentiate the equations, then you put one value and you get the another. When it is asked about changes. Is this clear?
Ma'am?
Yes.
The standard equation is ID is equal ID is equal to IS into exponential of VD by VT, correct? Now if we differentiate with respect to VD,
yes.
So which parameter, there are some constant and there are some variables, correct, in the equation?
Yes. So we are considering VD is the only variable, all others are constants. And considering
only, yes, all others are constant.
Yes.
VT is constant, IS is constant.
Yes. Considering that, we have differentiated.
Okay, DID, okay, divided by, okay.
Yes.
VD by VT, okay. Okay.
Okay. Chalo. Let's move on to the next problem. You can go through the notes as well as the lecture, and in case you have doubts, you can come up in the next session and we can solve it. So yeah, in this problem, what is asked? So it is asked that, okay, in continuation of earlier question, okay, there was another question, they got shuffled, yeah. So wait, actually these questions are shuffled. I'll maybe... Okay, yes. In this particular question, this is question number 9. So we have 10 questions today. This is question 9 and the last one is question 10. Yeah, this one is 10. Okay. So in this particular question, the circuit below has this IS, VT and R value, a voltage of 1.2 volts, 1.24 volts is applied across the circuit, and now the voltage is increased by 10 millivolts. So delta V is given to be 10 millivolts. What will be the increase in current? So in this particular problem, it is asked that delta V has already been given, V is given, so you have to find delta I. So okay, so in this problem, ID is I is exponential V by Vt. This is V by Vt, and R is given to be 4.92 kilo ohms, 4.92 kilo ohms, and Vd, is it mentioned? Vd is mentioned somewhere. Okay, Vd is not mentioned. So considering Vd as 0.65, as in other problems, in some problem it was mentioned.
Absolutely, it is given in the beginning of the question.
Right. Yeah, that's right.
If not mentioned, consider Vd to be 0.65.
Yeah. So in some problems, if in some problems one value is given,
not specified,
so you can consider that value. Yeah. So 0.65. So so if Vd is 0.65, so the voltage across R will be simply 1.24 minus 0.65, which turns out to be 0.59, yeah, 59 volts. And with this voltage, if we calculate the current across VR, it will be 0.59 by 4.92 milliamps. So IR turns out to be 0.12 milliampere. So this is the current that we get. So IR, now IR equal to ID. We know that IR equal to ID, so it will be 0.12 milliamperes. So if we want to make it as a resistor divider sort of circuit, so we can find the internal resistance of diode, which is called RD, and we can find RD as Vt by Id. Okay, so this is the formula. It must be, you might have encountered this formula in the lecture as well. So RD is Vt by Id. So we'll simply substitute the values 0.025 by 0.12. This is volt, but this is milliamperes. So it, let's use the same units. So 25 millivolts by 0.12 milliamps. So RD turns out to be
208.33.
yeah, 208.33 ohms. So total R total will be RD plus R, which is 0.208 plus 4.92 kilo ohms. So with this R total, that is 5.128 kilo ohms. With this R total, we have delta V, that is 10 millivolt. So delta, for delta I, it will be delta V by R total. So that is delta I will be 10 milli by 5.128 kilo ohm. So delta I is 1.95 microamperes. So this is how we have found the delta I, which is 1.95. Okay.
Excuse me, I think this is inaccurate, because we have to, the load line is what is the most important. Like when we draw the characteristics along with the load line, so the place where it intersects, that is the operating point for this circuit.
Right.
Here, like you randomly assumed that okay, the VD is actually 0.65, whereas for this current, it might not be 0.65, right?
No. So VD, why we assumed VD as 0.65? Because in earlier problems, there were few problems where VD was already mentioned as 0.65. And since in this particular question it was not given, but if you see, so if you have, let's say, a pool of 10 questions in your assignment itself, but there is a variable in few questions it is mentioned, and in few questions it's not mentioned.
Now you should put back the value that for ID and IR that you have got back into this equation and verify that, okay, VD is actually like, you should put this VD back into this and see whether you get this ID, right? Then only it will be a
right. So you are saying like the way we did it for the first iterative problem for diode, we should have checked it here as well. That's what you are saying.
Yes, I think maybe this is why I am not getting the right answers. Like,
Ma'am, in fact, I'm also stuck up. I got very funny answers. I mean, answers which are not at all matching with your, the options given here. So I was also struggling.
Okay.
Quite a lot. Yeah. So some of these values are somehow, I don't know, somewhere mismatch is there, or somehow, in fact, I may not have understood properly. That may be the reason. But the values are many times not matching. If you go by the standard electrical circuits or anything, because nothing but the standard electrical circuit, only the diode comes in the picture, drops are there across diode, that you have to consider. Correct, ma'am?
No, drop, see, we have always considered the drop, but I understand the problem of self-consistency that you are saying, that we did in the first problem also. We have gone till 3 iterations. But the question is it wise to always go through multiple iterations to solve a problem, because it will definitely consume your time a lot.
That's right, ma'am.
So in that question it was specifically mentioned that you have to use the iterative problems, so we went ahead with that. But I understand that there might be a consistency issue if we go by this particular situation, because if you
like in the problem, they should mention very clearly that, okay, use the normal cut-in model or use the ideal model. That they should make it clear, because
I have a feeling, why don't you check it once? Why don't you cross-check the ID with 0.65, because the values of IS and VT both have been changed in this particular question. Why don't you check
it across, like using some Excel solvers and all, like the answers are totally different. Like I just put the formula in the Excel and just vary the VD and the ISS, and it like comes out quite different from the available option.
Okay, can someone just pick out your calculator and check this for me? What are you getting the value of ID for this particular expression? 5 into 10 to the power minus 11 exponential 0.65 by 0.025 milliamps. Yes. Because in that particular question it was strictly mentioned that you have to use iterative method, so we went ahead with that. But most of the times we try to avoid iterative method, because sometimes it ultimately depends on how close your guess is. Like if you, instead of 6.2, if you have taken, let's say, 6, then first you might get 6.2 or 6.7, then you will get 9.9, then you can, so it might be, sometimes iterative methods may take you till 4, 5, 10 stages, and exam the questions are designed that are not so computationally extensive for a person, rather they are more like straightforward and easy to solve. That is what my observation is. So, but yeah, so did anybody check this, ID, like what is the value of ID that you are getting?
So like I have got some sort of Excel calculator, like if you want I can share my screen and like I can show you how I have done it. Like
no, I understand your feeling. I'm just concerned, like in this particular question, do the values really satisfy or not? For this particular,
it is coming 9.78 milliampere.
9.78 milliamperes. So that's completely off then.
Yeah, that's the problem, ma'am.
Okay. This is 0.12. This is correct, right?
Yes, this 0.12 is correct.
0.12 is correct.
Because we are assuming that 0.65, so subtracting that, it will be correct.
Right. And the funny part is, so this solution, I've got this solution from NPTEL itself, and they solved it this way, and I was like, okay. But yeah, for this particular question, I didn't check it through iterative method because it was not mentioned. So I was like, there is no need for the wastage of time. That's why I didn't check it. But okay. So here they have basically tried to use the dynamic resistance concept of diode, and they tried to solve it. So that was the basic gist out of this problem. So what was new in this problem was they wanted to introduce this particular thing. RD is VT by ID, and with this they have tried to find the resistances, and from there they have tried to find the change in current. Okay. Why don't you, okay, since we are lacking in time, why don't you try one more method? See, here also we had to find DI, right? Earlier also we found DI, right? Here. So why don't you consider this particular method that we did, differential wala, and you solve and try to find DI and see if you are getting the results in this, like with this method of differentiation wale mein. Maybe you people can try and let me know in the next session.
Yeah, ma'am.
Okay.
Yeah.
So you try this differential wala method and let me know if this is giving the correct result. So the correct results which was mentioned, which was given by NPTEL was also 1.95, and the catch in this problem was they wanted to use this dynamic resistance model. So VT by ID, they tried to use this, and they have solved the problem. But try to use this DI by DV problem that we solved earlier, and from there let me know if you are getting the results correct. Okay, in next week.
Ma'am, one doubt now.
Sorry, yeah.
Eighth question.
Eighth question. Okay. Yes.
Ma'am asked me, why did we have done VD by VT?
VD by, so it was asked like change in diode current with change in VD. So that was the question.
No, actually it will be 1 by VT. VD will not be multiplied.
Sorry?
VD will not
Absolutely.
be multiplied.
Ah, yeah, right.
No, VD won't be there, ma'am.
Yeah, it will be constant, right?
Yeah,
so 1 by
that delta VD you are taking it down.
Yeah. So this delta VD has come down, no? So यहाँ पे जो ये 2 ये आ रहा है 2 MV, so that is because of it's like I have taken this VD over here. So उसकी वजह से it has become like delta ID is ID into delta VD by VT. So that is why it has become like that. Yeah. So try it with this method, no? ये जो last problem था, question number 9. Try it with this method and let me know if you are getting the answer as 1.95, which is actually the answer. This is the correct answer which is given by NPTEL. So let me know if you are getting with this method.
Okay.
Okay. So meanwhile, let's move on to the last problem. So in this problem, it was the same problem from earlier. So here you have to find the value of ripple. So for ripple across this, so ripple needs to be found out across this. So the first idea is you have to find the RD, you have to find the Z, then RD in series with Z, so it is like RD in series with Z, and you have your supplies. So across this you have to find the voltage. That is the idea. But this problem is actually a quite lengthy problem. So you have to go through like transfer functions, you have to solve the transfer functions, then its magnitude, and in that magnitude you have to put the values, and finally we'll get this V out. So yeah, that is the question.
Again,
So,
like in this problem also, the exact operating point is sort of like different, because I struggled a lot and I never got the correct answer.
So in this problem, the correct option is B. Okay, what operating point is not given. In addition, 1.2 volts is given, 10 cos omega. Omega is given, C is given, and here also R is given, C is given, and RD we have picked from earlier problem. This RD we calculated, right? 208.33 ohms through, like, RD equal to VT by ID. Yeah, from this we calculated it as 208.33 ohms. From there this RD was calculated and then it was solved. So ultimately you have to find like mod VR by V in this problem. Mod VR by V needs to be solved. That is the question. So VR, like voltage across R. So VR by V, this is what needs to be solved in this problem. But the main problem again arises is that the RD value that we are getting as 208.33, that is coming because of the ID of 0.12 milliampere, which we were saying like from this ID equal to IR. But the concern is when we are not getting this, how will we proceed to this problem, right? Okay. Because the whole problem here we are stuck with is ID, like consistency of ID, no? Okay. We have to, if we have to go for iteration, okay, so let's do one thing. In this particular problem, question number 9, for di by dv, we can use that earlier question number 8, this concept, and from here we can get the delta I and check whether the delta I we are getting is correct from the one which is given in the options. One thing. Then secondly, the main concern that arises because of the assumption of VD is ID value, and so ideally the way here in this question that we did, no, question number 5, in this question also the same concern was there. The ID which we were getting out of formula and IR which we were getting, they were not consistent, they were not equal. So ultimately we were doing iterations to get them consistent and equal since they were in series. Since the circuit is same, so the concept should also be same, right? So the same current definitely has to flow through ID as well as IR. So what we can do is we can again use the iterative method there as well to make sure that the currents are equal. Then whatever the current that we are getting, from that current we can find this RD and we can proceed further. So these are the two methods that we can move forward, and we can then see how different the results are from the one which has already been reported. So this is what we can do. Okay, so next week maybe we can take up this question number 9 and 10 again, right? But question number 9 and 10 with the new methods of like we can solve them through our understanding rather than going with the solutions which are already provided by NPTEL. We can go with our understanding and then see what we are getting. Okay. So let's take up question number 9 and 10 next week as well, and with that we'll take up the problems for week 2 also. Is it okay?
Yeah.
Because I feel there really is a discrepancy. It was not mentioned, so I didn't cross check, but yeah, maybe we'll take up this problem and solve it with iterative method 1 and DI by DV method 2. And once we get question number 9 correct, the question number 10 is actually linked with question number 9. So if 9 is incorrect, so 10 we cannot get a correct result. So we can take these 2 questions next week. With that, we'll take up next week's questions as well. Okay?
Okay, ma'am.
Thank you, ma'am.
Thank you everyone.
Thanks for your time. Thank you.
Thank you so much for joining. You can see the recording. So recording has already been done. I'll immediately start uploading it in the YouTube, and I'll share the link with the PMRF people. So you might see that sheet, like where you can see the documents being uploaded as well as the link for YouTube. Is there any sheet that has been shared with you people?
No, ma'am.
Not yet. So they might share it very soon. So there is a sheet that we have to prepare where we upload our document, like this written document that I am preparing right now in front of you, as well as the link for my YouTube video. So this complete video will be there in the YouTube. So you can refer to that as well anytime. Okay.
Okay,
thank you, ma'am.
Thank you everyone. Have a wonderful evening ahead. Thank you. Let's meet next week.
Yeah.
Thank you. So maybe I'll end the session. Thank you
so much.
Thank you. Maybe I'll end the section here. Let's meet next week at the same time, Monday 6 to 8.
Sure.
See you everyone. Bye. Have a good
Bye.
evening.
Have a
Good night.
Good evening.
Bye.
Have a good evening too.